Welcome back. Now that we have warmed up a bit to the concept of machine learning, in this video I'm going to discuss different types of learning methods out there. Think about this video as a glossary that you can refer to when you start a machine learning project and you'd want to decide what approach to choose. You could think about types of learning from different perspectives. First of all, you can think whether or not they're trained with human supervision. And this perspective includes the methods called supervised learning, unsupervised learning, semi-supervised learning, and reinforcement learning. We are going to go in more details later during this lecture about these topics, but for now skip this and see what are the other perspectives. Another way of looking at different types of learning is to see whether or not they can learn incrementally on the fly. And this is what we call batch learning and online learning. Batch learning is when we have all the data, and online learning when we are doing it incrementally. More on that later. And finally, we could have this perspective that whether the algorithm work by simply comparing new data points to known data points, or instead detect patterns in the training data and build a predictive model, much like scientists do. And the first approach is called instance-based learning, and the second one is called model-based learning. As I said, we are going to go through these different perspectives later during this lecture. Keep in mind that these criteria are not exclusive. You can combine them in any way you like. For example, a state-of-the-art spam filter may learn on the fly using a deep neural network model trained using examples of spam and healthy emails. This makes it an online model-based supervised learning system. So you see, we mixed three different types of learning into one single machine learning project. Okay, now let's look at each of these criteria a bit more closely. And we start by supervised learning. In supervised learning, the training data you feed to the algorithm includes the desired solutions called label. In this example, you see our training data comes with two different labels, apples and cupcakes. So by this, we know even the unseen data that we're going to predict in future what they are either apples or cupcakes, and this model is basically predicting that, giving an input, what is the label for an unseen data. A typical supervised learning task is classification, and again, similar to what we had during this lecture, the spam filter is a good example of this. It is trained with many example emails along with their classes, a spam or healthy email, and it must learn how to classify new emails. So this is an example of supervised learning. Another typical example is to predict the target numeric value. So supervised learning could be used to predict numerical values. For example, the price of a car, given the set of features, it could be a mileage, age, brand, and we call these feature predicators. This sort of task is called regression. To train the system, you need to give it many examples of cars, including both their predictors and their labels, which are their prices. So as you saw already, supervised learning could be seen as a classification problem, which is predicting different classes of the input data, or it could be seen as a regression problem, predicting a numerical value associated with a set of input features. Uh, Now, let me give you some bit of theory. It's not really that complicated. It's just putting all the words that I said into some sort of scientific formulation. So in supervised learning, the data set is a collection of labeled examples, tuples of xi and yi's, where I ranges from 1 to n. And each element xi among n is called a feature vector. And a feature vector is a vector in which each dimension j from 1 to d contains a value that describes the example somehow. And that value is called a feature and is denoted as xj. If I want to give you an example, for example, if we assume x in our collection represents a person, then the first feature x1 could contain height in centimeter, the second feature x2 could contain weight in kilograms, and x3 could contain gender, and so on. You can really continue the list with whatever feature you have in mind. And for all examples in this dataset, the feature at position j in the feature vector always contains the same kind of information. It means that if x2 for x2i contains weight in kilogram for some example xi, then xk2 will also contain weight in kilogram in every example xk k from 1 to n. Okay, what about label y? What about yi? Yi is actually our label. The label yi can be either an element belonging to a finite set of classes, 1 to c, or it could be a real number, or a more complex structure like a vector, a matrix, a tree, a graph. Basically, it is our output feature. And unless otherwise stated, at least for this course, yi is either a finite set of classes or a real number, and you could already guess when we have a set of classes, we have a classification problem. When we have a real value, we have a regression problem. If I want to give you an example, for example, we are thinking about our email messages, and the problem is spam detection. Then we have two classes, spam and non-spam. And the goal of a supervised learning algorithm here is to use a data set to produce a model that takes a feature vector x as the input and outputs information that allows us realizing the label for this feature vector. For instance, the model created using the data set of people could take an input feature vector describing a person and output the probability that the person has cancer or not. So these are two different examples that we had here. And there are some famous, fundamental, very well known, whatever you want to call it, supervised learning algorithms. Supervised learning algorithms by no means are limited to this, but these are some of the things that you're going to see during this course, and I have listed them for you here. So more details will come in later lectures during this course, and this include k-nearest neighbors, linear regression, logistic regression, support vector machines, decision trees and random forests, and neural networks. And you could also already, I think, guess from the name of some of them which of them are regression, which of them are classification. One thing to point out here is that names could be deceiving. For example, logistic regression is actually a classification method. Of course, it outputs a real value, which is the probability of something belonging to some class. So that is why it's called regression. But at the end, it basically classifies some input data. And as I said, we will discuss these algorithms in detail later in the course. So let's stop with supervised learning algorithms here and move to the unsupervised learning algorithm. And in unsupervised learning, as you might have guessed already, the training data is unlabeled. In the other word, the system tries to learn without a teacher. For example, you have a lot of data about your, let's say, weblogs visitor, and you want to run a clustering algorithm. Clustering algorithm is a form of unsupervised learning algorithms to identify the group of similar visitors. So you have no pre-notion what classes you're going to have of your visitors. And that is why we are using an unsupervised learning methods. There is no label. At no point uh, you tell the algorithm which group a visitor belongs to. And basically what the algorithm does is to find those connections without your help. For example, your algorithm could notice that, I don't know, 40% of your visitors love comics book, and those people generally read your blog in the evening, while 20% of your visitors are young sci-fi lovers who visit during the weekend and so on. An approach here could be using a hierarchical clustering algorithm, but this is what we're going to discuss later. Just in short, it may also subdivide each group in smaller groups. And it is useful in these specific examples because it will help you target your posts for each group of audience that you have identified using your clustering approach. So let's give you a bit of more scientific definition. In unsupervised learning, the data set is a collection of unlabeled examples. I ranges between 1 and n, and you have already noticed the difference between supervised and this is wrong. It's unsupervised learning. I'm going to fix that later. Uh, the difference between supervised and unsupervised learning is actually in the missing yi here. If you remember in the previous example, yi was denoting our labels, which is missing here. Again, like before, x is the future vector, and the goal of an unsupervised learning algorithms is to create a model that takes a vector x as input and either transforms it into another vector or into a value that can be used to solve a practical problem. For example, in clustering, the model returns the ID of the cluster for each feature vector in the dataset. And if I want to give you some famous unsupervised learning algorithms, uh, they could be k-means, hierarchical cluster analysis, expectation maximization, or principal component analysis. And they do different things. Not all of them do clustering, but the majority here at least do clustering. Okay, so we covered supervised, unsupervised learning so far. But what about semi-supervised learning? What are they anyway? Well, some algorithms can deal with partially labeled training data. And by that, I mean usually a lot of unlabeled data and little bit of labeled data. This is called semi-supervised learning. An example is, for example, Google Photos. This is a good example for this. Once you upload all your family photos to the service, it automatically recognizes that the same person A shows up in photos 1, 5, 11, while another person B shows up in photos 2, 5, 7. This is the unsupervised part of the algorithm, that is clustering. Now, all the system needs is for you to tell it who these people are, just one label per person. And then it's able, I mean, that is altogether 4 names, for example, and it is able to name everyone in every photo, which is useful for searching photos. I think you have seen something similar to that in your phones. uh, I know that iOS system has this, so there's a section that it groups the photos that are similar to each other. It even guesses that which person that is, and then you could assign the correct label, and after that you have the photos of all people that you have already put a label for them together. Okay, so let's move on. uh, In semi-supervised learning, the dataset contains both labeled and unlabeled examples. And usually the quantity of unlabeled examples, as you have already seen in the previous example, is much higher than the number of the labeled examples. And the goal of a semi-supervised learning algorithm is the same as the goal of the supervised learning algorithm. The hope here is that using many unlabeled examples can help the learning algorithm to find a better model. Of course, it could sound counterintuitive that learning could benefit from adding more unlabeled examples. It kind of seems like that we are adding more uncertainty to the problem. But the reality is, when you add unlabeled example, you add more information about your problem. A larger sample reflects better the probability distribution that the data we labeled came from. Theoretically, a learning algorithm should be able to leverage this additional information, and this is the reality in many cases, of course. So, so far, we have been looking at the perspective whether the algorithm used human supervision or not. We covered supervised, unsupervised, and semi-supervised learning. There is one last category here, and that is reinforcement learning. And reinforcement learning is totally a different story. The learning system, called an agent in this context, can observe the environment, select and perform actions, and get rewards in returns. Or, of course, it could be penalties, which we can consider negative reward. It's very much similar to how we learn in reality. We do something. If the feedback was good, we continue doing that. If it was not good, we know not to do that again. Like when the kids touch fire, it burns them. They don't touch fire again. Most of the time, of course. So this is, in a nutshell, it what reinforcement learning. It must then learn by itself what is the best strategy, and that a strategy we call it a policy to get the most reward over time. And a policy defines what actions the agent should choose when it's in a given situation. For example, many robots are good examples of reinforcement learning. They learn how to walk, for example, with these algorithms. A very famous example, and you're seeing it here on the screen, is DeepMind's AlphaGo program. It's, if you remember, of course, if you don't remember it, back in March 2016, but you probably heard about it later. It beat the world champion Lee Sedol, if I'm pronouncing the name correctly, at the game Go, and it learned its winning policy by analyzing millions of games and then playing many games again itself. And keep in mind that learning was turned off during the games against the champion, so it was what it was. It couldn't learn again. The AlphaGo was just applying the policy it had learned by analyzing games before. And if we want to get a bit more technical, you don't see any uh, letters here really, or formulas. Reinforcement learning is a subfield of machine learning where the machine lives in an environment which is capable of perceiving the state of that environment as a vector feature. So we have these feature vectors everywhere. The machine can execute actions in every state. Different actions bring different rewards and could also move the machine to another state of the environment. So one action could be doing something in one state. It could also be telling the system move from this state to the next one. And the goal really in a reinforcement learning algorithm is to learn a policy. And as I already mentioned before, a policy is a function similar to the model in supervised learning that takes the feature vector of a state as input and then outputs the optimal action to execute in that state. And we call an action optimal if it maximizes the expected average reward. Uh, Reinforcement learning normally solves a particular kind of problem where decision making is sequential and the goal is long term. It could be game playing, it could be robotics, it could be resource management, logistics. Many autonomous driving examples are using reinforcement learning one way or the other in them. And by this, I conclude this first perspective to types of learning. I hope you have still energy for a few more perspectives. They are probably not as detailed as this one. So, the second one is the the perspective when thinking about the data, batch learning versus online learning. This criterion used to classify machine learning system whether or not the system can learn incrementally from a stream of uh, incoming data or not. So let's start by batch learning. In batch learning, the system is incapable of learning incrementally. It must be trained using all the available data. So you cannot come in and say, okay, I give you this portion of the data and wait to see how you perform. You mean the machine, and then I give you more data. So everything comes as a big batch at the beginning. And this generally will take a lot of time and computing resources. So it is typically done offline. First, the system is trained and then it is launched into production and runs without learning anymore. It just applies what it has learned. That is why we also call it offline learning. If you want a batch learning system to know about a new data, such as a new data spam, you need to train a new version. So the whole thing should happen from scratch on the full dataset again, and then stop the old system and then replace a new one. And of course, fortunately, the whole process of training, evaluating, loading machine learning system could be automated fairly easily. So even a batch learning system can adapt to change. Uh, you simply need to update the data and train a new version of the system from the scratch as often as needed. But keep in mind that that step should be in, and it is basically doing it all over again. This solution is simple and often works fine, but this training sometimes could take long. And you probably need to train your system, I don't know, every 24 hours, sometimes weekly. So if you want your system to adapt to rapidly changing data, then probably batch learning is not your solution. Sorry. Okay. And finally, if your system needs to be able to learn autonomously and it has limited resources, that it's not really a good idea, and it could become a showstopper. So what is online learning then? It is probably a better solution in the situations I just described. In online learning, you train the system uh, incrementally by feeding it data instances sequentially, either individually or by small groups called mini batches. Each learning step in online learning is fast and cheap, so the system can learn about the new data on the fly as it arrives. And if you have limited computing resources, uh, once an online learning system has learned about the new data instances, it doesn't need them anymore, so you can discard them. Of course, keep in mind that if you want to be able to roll back to previous state and replay the data, then you need to keep them. And this can save a huge amount of space for you. Online learning algorithms can also be used to train systems on huge data sets that cannot fit in one machine's main memory, and this is what we call out of core learning. The algorithm loads part of the data, runs a training step on that data, and then repeats a process until it has run on all of the data. One important parameter of online learning system is how fast they should adapt to the changing data, and this is called their learning rate. If you set a high learning rate, then your system will rapidly adapt to new data, but it will also tend to quickly forget the old data. You don't want a spam filter to flag only the latest kind of spam it was shown. Conversely, if you set a low rate, then the system will have more inertia. That is, it will learn more slowly, but it will also be less sensitive to noise in the new data or to sequence of non-representative data points. So it is on you really. What is it that you want from your system? Is it high learning rate suits your purposes better, or low learning rates? Well, it's not all beautiful and rosy. There's a big challenge with online learning, and that is if bad data are fed to the system, then the system's performance will gradually decline. If you're talking about a live system, your clients will notice, for example, bad data could come from, I don't know, a malfunctioning sensor on a robot, or from someone spamming a search engine to try to rank high in search results. And to reduce these risks, what you need to do is to monitor your system closely and promptly switch learning off, and probably reverting to the previous working state if you detect a drop in the performance. You may also want to monitor the input data and react to abnormal data. That is something that we call and could be done using an anomaly detection algorithms. So this perspective had to do with the flow of data when we are doing learning. The next one is by how they generalize. It is instance based model learning versus model based learning. And this is another way to categorize machine learning systems. And as I said, it is by how they generalize. Most machine learning tasks are about making predictions. This means that given a number of training examples, the system needs to be able to generalize to examples it has never seen before. And having a good performance measure on the training data is good, but it is not sufficient. The true goal is to perform well on new instances. There are two main approaches to generalizations, one instance based learning and the other one model based learning. So let's start by instance based learning. Uh, well, I mean, possibly the most trivial form of learning is simply to learn by heart. If you were to create a spam filter this way, it would just flag all emails that are identical to emails that have already been flagged by the users. Not the worst solution, but certainly not the best. It's basically identify criminals, but by previously known criminals. You catch the known ones or the ones that are very similar to them, but not the new ones. So instead of just flagging emails that are identical to known spam emails, your spam filter could be programmed to also flags that are very similar to known spam emails. Of course, this requires a measure of similarity between two emails, and a simple measure could be to count, for example, the number of words they have in common. Then the system would flag an email as a spam if it has many words in common with a known spam email. This is called instance-based learning. The system learns by the examples by heart, then generalizes to new cases using a similarity measure. This is not the only way of generalization, as I said. The other way is model-based learning. What it happens here is that we generalize from a set of examples to build a model out of these examples. Then we use this model to make predictions. And this is what we call model-based learning, really. I can give you an example here. For example, suppose you want to know if money makes people happy. So you download the Better Life Index data, as well as the stats about their GDP per capita. And then we join them in a table as you see here. What we do next is we will plot this data, and let's see if we could see a trend. There seems to be a trend here. Of course, the data is noisy, it's kind of partly random. It looks like life satisfaction goes up more uh, kind of linearly when the country's GDP per capita increases. So let's decide that the model life satisfaction is a linear function of GDP per capita. And this step is called model selection. This is what we're doing now. We're selecting a model. We selected a linear model of life satisfaction with just one single attribute, GDP per capita. And this is an important step. Model selection is important. You need to have an understanding what you want to know, have an understanding of the data, and then what sort of model suits your data better. By learning more algorithms when they are suitable for what type of data, you're going to get good at this. But for now, just accept my word that you're going to have a linear function here, and I have written the function that I have in mind. This model has two parameters, theta 0 and theta 1, and by taking these parameters, we can make the model represent any linear function. So it is simple. Basically, it is what we said. We predict a value of life satisfaction based on GDP per capita plus some parameters. And before we can use the model, we need to define the parameters theta 0 and theta 1. And how can we know which value will make the model perform best? For this, we need to specify a performance measure or a fitness function that measures how good the model is, or we could define a cost function that measures how bad the model is. For linear regression problems, people typically use a cost function. And what cost function does is basically it tells what is the distance between the linear model's prediction and training values. And in this graph that you see here, we have drawn with different theta values, theta 0, theta 1 values, different lines, different linear functions, and some of them are like dramatically bad. They're not even close. But the one that there is not that much distance from the data points is the one that you see on left. And the objective, as I said, is to minimize the distance. And this is where the linear regression algorithms comes in. We feed in the training example and it finds the parameters that make the linear model fit best to the data. This is called training the model. And in our case here, the algorithms finds the optimal value to be theta 0 4.85 and theta 1 4.91 multiplied by 10 to the power minus 5. And now the model fits the training data as closely as possible, and this model, this linear function that we built, could be used for predicting the other life satisfaction values for the GDP per capita we haven't seen yet. So if somebody comes with a GDP per capita that was not part of our data set, we could predict as closely as possible the life satisfaction value for that country. And by this, I wrap up different types of learning. Uh, Next session, we're going to discuss about fundamental algorithms. We have seen the list of some of them here. We're going to describe in details what they are. We're going to practice coding about them. Then we're also going to get to anatomy of learning algorithms. What are different parts of a learning algorithm, and this is very important. It's going to give you an insight on what you need to tweak when you want to get a better performance. We are going to talk about gradient descent and how machine learning engineers work. So by this, I say goodbye to you for this lecture. Remember to check the videos on practicalities so you know how the course assignments are evaluated, how many assignments are there, about online meetings, about the foreign bonus points. Don't forget to check out those videos as well. See you in next lecture next week. Good luck with learning machine learning. Bye.